Problem 3.1. A car traveling at 25 miles per hour accelerates to 65. So it's going slow and then goes faster. And the car does that in 6 seconds. Basically, they're giving us the time. So we have VO, but we have miles per hour. Do you see miles per hour? That is very common in cars, especially here on the border, right? We have our cars, they have miles per hour, some of them. So we convert that into meters per second. How do we do that? Okay, I did it this way. You can do the direct conversion, but I just wanted, I like it like this. So I have 25 miles per hour. I first convert the miles per miles, you see here, and I put them on the bottom, and I know that 1 mile is 1.609 kilometers. There's an M, should be a meter there. And then I know that kilometers per hour are converted, divide them by 3.6, which is the conversion of kilometers, and then 3,600 seconds to convert the hours. And the result is 1 over 3.6. And this is the conversion already done. We do the same for the 65, which is going to lead us to 29.05 meters per second. Remember to round. And we have 6 seconds of time. So they are asking us the acceleration in meters per second square. So the acceleration, if it's moving, we use the equations for kinematic equations. So which one is the good one, or which equation is the one that we're going to use? From equation 2, it gives us final velocity, initial velocity, and acceleration in time. We don't have distance, so we cannot use 1 and 3. From here, we solve for A. We already know how to do that. So we got the equation of acceleration here. And we only put the data. Now, remember just here that we have final here at the beginning, that we have the initial here over 6 seconds, and we will get an acceleration of 2.98 meters per second square. That's it. Let's go to the next one. This one, problem 3.2, a car traveling at 75 miles per hour. We need to convert that, we know. Hits on the brake, slams on the brake, so basically it's stopping. What is going to be, this is very important because we need to know that the final velocity is going to be 0. The initial is going to be 75, and we convert that, again, the same way that we did it on the other problem, to meters per second. And then we have 6 seconds, again, same seconds. And they are asking us for acceleration, so we use the same equation. We already set up this one. So it's the acceleration equation. And in this case, the only difficulty might be that the final is 0. The final velocity is 0, and the initial is 33.52, sorry. And then here the time. That's it. We calculate that, and we get 5.59 meters per second square. Let's go to the next one. There you go. Now, 3.3. How long does it take a car to cross 25 meters? Now it's different. We get here, we got distance. After the light turn green, the car accelerates from rest. So again, from rest, so VO is 0. We have a D of 25 meters, and we have a constant acceleration. Get it? So the acceleration is basically here 2.5 meters per second. They are asking us how much time will it take that car to cross that 25 meters with that acceleration. And what equation shall we use? Well, we have distance, so we can choose either 1 or 3, right? And we have VO 0, so the best one to use is, because we don't have final, so we need to use the equation 1. So this is going to be 0, and we only are left with this because we need time to leave time alone. And that time is going to be 2 times D over A, and you might remember this equation. We have used it many times. So the time is going to be, just put the 25 here, the distance, the acceleration, and we will get 4.47 seconds. That will be it. Let's go to the next one. In this one, it says a gargoyle. Whoa, those from the Notre Dame. It falls to the ground because it was an old building, right? The French, sometimes they don't do the maintenance. They do, but just bear with me. Okay, so it's telling us how far, so it's asking about distance, how far it will go in the second 1, 2, and 3. And there you see, I have a shorter distance for D, then a longer one for the D1, sorry, for D2, a longer one, and then a longer one. Oh, like this difference here is the one I'm checking for distance 3. And also they are asking us the velocities on this 3 times. And this is a problem is on the slides if you want to check it out. So from equation 1, because why 1? Because we don't have final velocity and we have distance, so we use equation 1. We have initial velocity because it was it didn't have any velocity when the gargoyle started falling. And we have that. The distance is going to be just 1/2 of AT squared. So we get that. D1, 1/2 of A, which is 9.81, is gravity, remember, because it's free falling, and time 1 second to the square. So it's going to be 4.91. We do the same thing. We just change the 2 here for the time, and we change the 3 for the time, and we get this results. They are squared here on the bottom. So let's go to the next one. Now, the second or part B, the velocities. What do we want? We want the final velocity, so we need to use either 2 or 3, equation 2 or 3. But we don't have the distances, and it's better because the time is given. And so it's better for us to use equation number 2. So we got final velocity, and we know that the initial velocity is 0 because it started without motion. And basically it's AT. That's it. 9.81 times 1 second. 9.81 times 2 seconds. 9.81 times 3 seconds. And we got those results. And that will be it. Nothing more. Let's go to the next problem. Well, let's do this problem. This is problem 3.5. A person throws a coin upwards, yes, and with an initial velocity of 10 meters per second. So basically, when it goes up, it has, let me do this to remind you. When you throw something with an initial velocity, it goes up, 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 and then we have a VO equals to 0, right? Is equal to 0. We have no velocity, and then let me choose another color. It starts going down, 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 and at the end, at the end here, we will have the same initial velocity, but this will be final now, and so it's easier for us to start on the top. Start on the top with a VO equals to 0 and something that is just falling. And at the end, we will have the final velocity. Here's a diagram of that. Here it is. There you go. We have the time. We don't know it. They're asking that. We have distance. And we have initial velocity equals to 0. We have G going down, right? It's a velocity going down, an acceleration going down. And then we have final velocity, which is going to be 10. This is easier, and we have already discussed that in class. Okay, now what do? We get an equation. We already have distance, so we use 1 or equation 1 or equation 3. So let's do one first. Let's start with the time. Here, if the time, well, we can use this equation, which is the second one. We have VO equals to 0, so we cancel it. So time is just final velocity divided by acceleration, which is 10 divided by 9.81, very simple. So we have 1.2. But remember that that is the time just for falling. But we also have the going up, right? So is the total time is going to be 2 times t, which is the time going down. So it's 2 times 1.02 is going to be 2.04, and that is up and down. So that will be the first part. The second part is very simple. Now we use the third equation. On this third equation, we still have VO equals to 0, so we solve for D. So it's going to be this one, VF squared divided by 2A, and we have it here. So we'll have 10, which is the final velocity, to the square, and then divided by 2 times 9.81, and we will get 5.10 meters. That will be the distance, or the maximum height. We can call it Y max. Remember, I can write very well with this thing. It's very difficult, but again, that's Y max. So let's go to the next problem. Here, this is, we have again the adventures of Zapotencio, right? And Zapotencio, he has, now he goes skydiving. And he goes in a plane. This is the plane which goes at a velocity of 300 kilometers per hour. We need to convert that into meters per second. That we know how to do that already. So we have an altitude of 12,000 feet, and we do have to convert that into meters per second, meters, right? So we have 12,000 feet. We have one foot is 12 inches. 1 inch is 2.54 centimeters. We go canceling here with the feet. Cancel the inches, and then the centimeters with the meters is 100 meters. So we all have a distance, a height. Let's call dy, or you can call it height or whatever. So this is the vertical height is 3,657.6 meters. Then what do we do? Okay, so let's go. We already have that conversion, so we use equation 1. Why 1? Because we don't have final velocity, so we cannot use 2 or 3. So we know that when the wheel, if you read the problem, the wheel falls from the plane, they will have trouble that. And basically what we have is we need to take that the time. So leave it alone, solve for that, and you will end up with 2 times d over the acceleration and g. And plug in the numbers, you'll end up with 27.3. Why it's a lot of time, almost half a minute? Well, because it's at a very high altitude, that's why. Now in letter B is very simple. We are asked this distance, the horizontal distance, and we only have this simple equation of, because we don't have acceleration in x. So we have BOX equals the distance over time. We solve for distance, so it's BOX time, because this goes to the other side. And we plug in the numbers here. 300 and 1 over 3.6, which is the conversion for this kilometers per hour to meters per second. And then we have the time, which is 27.31. We already have it here. So we can get the dx is 2,275.83 meters, or 2.3 kilometers. Basically that is it. Sorry, that is it. So let's go to the next one. This is very fairly easy. It's just the application of the formula of force equals mass acceleration. This is a Newton's simple one. They give us what they want to know: the force, right? The force. They want to. They give us the acceleration. They give us the mass. So we just put the mass and the acceleration, and we end up with this. We get 5 meters or 5 mega newtons, right? That will be it. This is fairly easy. This one, 4.2, certain net force. So we have a force. We don't know the force. Accelerates 10 kilograms, 20 meters per second. So let's find out that F. So we're going to call it F1, and it's a mass of 10 kilograms, and then 20 meters per second. That's the acceleration. Is 200 newtons. And then that same force will cause 5 kilograms. So F1 is going to cause another mass, a different mass, because it's different than 10, right? These are different. Yeah, these are different. And it's going to cause that to accelerate at what acceleration? So A2 is going to be the question. So let's see about that. We are going to solve for acceleration. Here's 2 missing. So acceleration 2 is equal to 200 newtons, which is the force 1, divided by the new mass 2, which is 5 kilograms. So it's going to be 40 meters per second. And it's fairly easy to see, because we have with a double, with half of the acceleration, we have the acceleration of 20. And when you reduce the mass in half, well, you need to compensate, so you double the 20 and you'll end up with 40. So let's go to the next one. Okay, problem 4.3. A car whose mass is 2,000 kilograms is accelerated uniformly from rest to a speed of, so this is speed of 15 meters per second in 10 seconds. So we have time, and we have the mass here, over here, mass. Kind of, yeah. And we have speed. The net force accelerating the car is, so they are asking for the force. The first thing we need to do is, okay, we have here the force equals mass acceleration. We want force is, we want it. We have the mass, ding ding, but we don't have the acceleration. But we do have some more information. We have time, we have final velocity, we have initial velocity. So from those, because we don't have distance, we can either use just equation 2. That's it. So we use equation 2, and equation 2 is this one over here. We solve for acceleration. So we have final velocity, yes, we have it here. Then we take initial velocity to the other side, negative, and we divide by time. So we end up with this equation here. Now we solve for those. So we have 15 meters per second, which is the final velocity. 0 is the initial, because it starts from rest. Here it goes. And we divide by 10, which is the time. Here's the time. We end up with 1.5 meters per second. That would be our acceleration. Now that we have our acceleration, we go and plug it in to this equation. So we'll end up with force equals mass, which is 2,000 kilograms, times acceleration, which is 1.5. We calculated that here. That will be the multiplication with 3,000 newtons. So our force is going to be the net force accelerating the car. It will be 3,000 newtons. So let's go to the next one. Okay, this problem 4.4 is about a book, and this is fairly easy because it's the first one of action reaction, right? So we have a book on a desk, and the mass of the book is 1.7 kilograms. So do you see this book that we have here? It's a little it's on the top of a table, and is pushing the table down. Okay, so here we have a free body diagram, and we have the only forces that we have is the normal force going up, and then we have the force of the weight going down. So we have the weight there, and from our equation from Newton's laws, we have that we don't have any acceleration, so acceleration is 0. We have sum of forces equals to 0. And the sum of forces is just the two forces that we have here, the Fn and W, right? So we put W, or the weight, we put it on the other side. So we realize that the normal force is going to be equal to the weight. And the weight, we know that it's mass times gravity, which is 1.7 times 9.81. And the normal force is going to be 16.60 and 68 newtons. Let's go to the next one. And this one, we have that problem is kind of the same thing. We have our book 1.7 kilograms, and we have also, we put another book on top of the one that we had. So what we have then is the same free body diagram. We have normal force going up, the resistance of the reaction of the table, and we have weight 1 and weight 2. The same thing, sum of forces equals mass acceleration. Acceleration is 0, so this term goes to 0. And then the sum of forces is normal force going up and negative weight 1, negative weight 2, so minus. We take them to the other side, so we carry this 2 and we put them on the other side. We change the sign, of course, and it's going to be W1 plus W2, weight 1, weight 2. We can calculate this, the mass of the first book times 9.81, the second book times 9.81, and we will end up with this normal force of 25.51 newtons. Let's go to the next.